Hello everyone, this is Amir from Audio Science Review. I have another debunking video for you. It's a difficult topic to address. It's a couple of papers that have come out from Professor Kunchur from South Carolina University. And normally it wouldn't be anything worth your time to worry about, except a couple of YouTubers have latched onto these papers. And here you see Jay Yuggy's YouTube channel, where he positions this thing as proof that there are measurable differences in audio interconnect cables, and that we can now objectively prove that there's audible differences between cables. It's a funny thing because we absolutely can measure differences between cables. The question is, do those measurements matter as far as perception? And the short answer is they don't. But I originally didn't mean to address this paper because it's just too much work to try to get into it. But multiple people have reached out to me and asked me about these YouTube videos and what people are saying about them. So I thought I'd go ahead and do a breakdown of the papers. Professor Kunchur has done actually 3 papers, one that came out a few years ago and it had very classic mistakes in it, claiming that digital audio resolution timing resolution is depending on a sample rate, which is just patently wrong. And then a few years went by and he produced a new paper, which I'm not addressing here because it turns out that he actually addresses it himself. And that paper came out last year and was published in AES, and it was phrased as cable pathways between audio components can affect perceived sound quality. And what he did was that he took a DAC and an amplifier and connected both XLR and RCA connections to the amplifier, and then AB switched the amplifier between the balanced input and unbalanced input. The implication of the whole paper is that he's showing the differences between the 2 cables. But in reality, first, the 2 cables are, one is a balanced XLR, the other one's RCA. But more importantly, the DAC and amplifiers have unknown transfer functions, frequency response, noise, and distortions between their balanced interconnects and RCA. So no way can you conclude whatever you're measuring out of this A/B testing that is relatable to the cable itself. Could very well be that the XLR connection had wider bandwidth, or the RCA one had more noise, or what have you. And so I and many other people objected to this and pointed out all these problems. And fortunately, the author starts with his newest paper acknowledging that this problem exists. So the introduction, and you can see the link to the paper here, he goes in there, and then he admits at the end, says, however, that approach prevented distinguish between noise between the pathways original from balanced versus unbalanced, or the cables themselves. Excuse me. Hallelujah. That's one of the many problems with the paper, with the first paper. So it's good that he's acknowledged this, but it's sad that AES published this after peer review in the journal. So that was a mistake on multiple fronts. So we now get into the second paper, or the third paper in sequence, and the one that YouTubers are jumping on. And what I'm going to do is to quote sections of it, and the paper is divided into different sections. It's only measurements. There's no listening tests in this paper. The last one had listening tests. This one does not have any listening tests. So it's purely measurements. So any claims about audibility is just claims. It's not backed by any listening tests in this final third paper. And what he does is that he tries to attack the problem of measurements from multiple vectors. And that's a good approach. And he actually says some of them are dead ends. And so what I'm going to do is that I'm going to talk about each section. So in the introduction of what cables he's testing, he says there are 3 different cables. One is a premium cable, one is a sort of a premium cable, and one is a generic freebie one. And I'll give you more details about this as he mentions them later on. And he implies that when you go shopping for the cables, you have these 3 distinct categories. But as you probably guys know, that there is no such There's no such grades in audio cables. There's no certification, and I can buy a $5 cable that could be fantastic as far as bandwidth and performance, and I could buy a $50,000 cable that would be horrific from point of view of performance. So the notion that he's just going to tell us that these are 3 generic categories and let's run with them, it just doesn't make any sense. Doesn't even pass common sense. As a minimum, he should tell us what these cables are so that we can go and replicate his measurements and testing. He doesn't even tell us what these brands are, the model, nothing. He just said we picked 3 cables, and one is, high, the other one's mid, and the final one is a cheapy freebie one. It's like, well, what kind of science is this, when we can't even go replicate? It would have taken nothing for him to mention these cables, but he does not. Okay, so let's get into them. The section 2.1 defines, it sort of says, let's treat audio as a low frequency problem, and low frequency defines up to 1 megahertz. Well, hearing stops at 20 kilohertz, so 1 megahertz is very high bandwidth for audio. You've already gone way past anything reasonable. There's nothing that can hear 1 megahertz or anything like that. Those are radio frequencies and AM radio. So that doesn't make any sense itself. Fortunately, he concludes that even if we go up to 1 megahertz, that if we measured sort of the losses and things like skin effect, they're at 0.001 dB difference, so therefore this doesn't matter. So it's like, hallelujah, yeah, that's good. And the paper should have really stopped here. There's nothing past this point. If up to 1 megahertz we can't quantify anything being a problem, then we're done on this thing. But this is just warm-up act. It goes from here. So then he gets into this notion that I've never ever seen, and he invents it and he just runs with it throughout the paper. There's this implication that every cable has capacitance, which it does. Anytime you have a conductor and insulator, you can get, and another conductor, you can get a very small capacitor gets formed in there where you can hold a charge. But he claims that this capacitor is instantly changing its charge, going from max to minimum or 0 to max. This is just absurd. No capacitor does this. Capacitors take time to charge and take time to discharge. Audio signals are extremely slow in the world of frequencies as a frequency. We can go to many gigahertz and higher, and we're talking 20 kilohertz the maximum what we can hear. And so nothing is changing fast in audio world. To say that the capacitance of the cable is instantly changing, and therefore we should go measure those instant effects, just assumption is just totally wrong. Nothing in your audio system would work if this assumption is true, because we have much larger capacitors inside your amplifiers and everything else. If those are instantly charging and discharging, well, then hell breaks loose. Nothing would ever work in electronics if that was the case. So the whole concept is ridiculous. And again, we could stop here. But for the sake of completeness and for you referencing it in the future, somebody jumps on these things and tries to, challenge you, you have this presentation to go back to, okay? So let's talk about where these things matter. There's this word transmission line is thrown around throughout much of the paper. The transmission line comes about if the signal's changing so fast, or the length of a transmission is so long that the waveforms for current and voltage start to get out of sync, and as they do, the effective impedance changes along the length of the cable. That complicates the heck out of our world, and indeed anybody designing radio frequency equipment has to deal with this thing, and it's a world to itself. People say there's combination of science and art. It's so difficult at times to design things that go up to gigahertz and higher frequencies, but even in many megahertz, it can be very challenging. Fortunately, if you look at when you have to apply this, There's some nice rule of thumb. And where do you get this rule of thumb? You go to the expert in the world of electromagnetic interference and compatibility and transmission. It's a book by Henry Ott. Henry is I don't want to say he's the Einstein of this world, but he's the gold reference authority on this. And if you want to learn anything about EMI and electromagnetic interference and so forth, get this book, as I have. And in there, he has this very clear rule that all engineers know about, is that you only worry about this transmission line effects is when the length of the wire is more than 1/10 of the wavelength of the frequency that you're dealing with. So if we apply this to audio, and we use the highest audio frequency we can hear is 20 kilohertz, that means transmission line effects only happen at 1/10 of this number, the wavelength, and that's 1,500 meters, so 1.5 kilometers before we have to treat audio as a transmission line. That's why the phone company in the old days, when we use wired phone lines, when I go from city to city, yes, you worry about transmission line effects even for voice transmission. But, in our world with, 1 meter interconnect cable, we're 1,500 times below this when this effect even starts to become significant. So any talk about transmission line effects for audio cables, interconnect cables, or any kind of audio cable, it just makes zero sense. It immediately is a red flag saying, whoever is saying this doesn't have a foggish notion of what they're talking about. Go talk to any RF engineers, any serious engineer, they'll tell you this thing. They'll laugh at you when you say audio cable is a transmission line. It simply is not. If you transmit digital audio over it, those pulses are sharp, and I'll talk about that, then the bandwidth gets higher. But for analog audio, it absolutely doesn't matter. And you can go up to 20 kilohertz to any frequency you want, 100 kilohertz, and you still can't get to anything close to these kind of things. And that's a great thing, because if you open up an audio amplifier or audio DAC, it has nothing in there that is designed based on these principles. Whereas if you open an FM transmitter or your cell phone, the RF section of that, you'll see all kinds of tricks in how even the smallest line or PC board trace is meticulously designed and drawn. And if you just touch that trace, everything stops working. Whereas I can touch an audio amplifier, inside, and nothing will happen. It'll just work just as well as it did before that. So again, we could stop here and say everything is going to talk about is absurd. But let's go through the practice of looking at the kind of testing he does, so you're educated when people try to pull a stunt like this on you. So, and here he not only talks about these transmission line effects mattering, but he also talks about these effects are nonlinear, therefore very complicated, and so forth. And then we've got some really absurd stuff. He says, look, you can deal with some of these issues by using ordinary, RG59 cables, or you could go buy this $2,000 or $3,000 North 2 cable. It's like, what? Who writes a paper like this where you mix a proper reference, like, a cable with certain interconnect, certain geometry, to also a North 2 cable? Really, I've got to make a reference to put this in the same sentence as these things. It just makes no sense. And this section, by the way, it deals with this whole notion of propagation speed through a cable, how close that is to speed of light, which is what the C is. And this whole thing is just a complete bunk. There's a company called Iconoclast, a spin-off of a guy who left Belden Cable, and makes this cables called the Iconoclast. I did a complete review, measurements, and a music null test where I show what the difference is between that and a dirt cheap junk cable. And a null test showed with real music content that there's absolutely nothing that this cable brings to table, even though it follows this whole assumption of propagation speed matters to a cable, where, not being exactly at speed of light, but a little bit below speed of light, and how it can vary from 20 hertz to 20 kilohertz. It goes a hair slower or faster. That can change the sound. Well, no, I've got, not only is this whole concept makes no sense, but again, I have done an exact review of a cable far more than the Nordust Norse 2 that is its entire focus around this thing. And I showed that with whether you look at the absolute measurements or null test of real music, it makes no difference whatsoever. Then there's this whole notion that, he says, oh, in the last paper we proved that noise is what impacted what people were hearing. That's totally nonsense. When you do an A/B test like you did between XLR and RCA cables, and some people, thought one sounded better than the other, that's not a cause and effect. That's an observation. You can't just say, well, I also measured the noise was a little bit higher in one versus the other. No, that doesn't mean the two are connected together. If you think noise is the problem, you generate noise and you vary the amount of noise and see if that is the controllable parameter in there. And by the way, noise is noise. You either hear it or don't hear it. You don't get this thing about this imaginary, sound state changing, or the highs all of a sudden sound this way or that way. And ironically, more noise can actually improve the perception of detail, and because it actually adds a sparkle to the high frequencies and makes them more brilliant. And so, like, those of you photographers may know this, that the film grain, in the old days when we used to shoot in film, if you remove that grain, oftentimes the image actually will look softer, because that randomness, that sparkle, actually made people think the image is sharper and better, not that it's worse. So his old assumption that more noise is worse is kind of absurd anyway. But again, there was no cause and effect whatsoever in his original paper. It's just him all of a sudden connects the two together. So here's some random invalid measurement about noise, and therefore that is the reason maybe people prefer this to that. So please don't fall for this whole section 2.4. So he now gets into section 3.1, gets into the cables again. And he says the first one is a $500 audiophile interconnect. Which one, we don't know. It gets into what his material is. It's like, whoop-de-doo, what do I care about that? Show me the specifications for that cable. Show me the measurements of that cable. Show me who made it, what it was. Not that it's $500. Then the next one is a $50 one, and it happened to be one of the ones where it's grounded at one end versus the other, so it's directional. And then the third one is some kind of generic cable you buy from a general store for $5. Really? There's these three buckets? I had no idea that the world had standardized on these three buckets. I could go get a sample of 10 of these freebie cables, and they would all have different characteristics, because each one was constructed differently, different material, different cabling. And for $10, you can get a video cable that has incredibly good bandwidth and good termination and everything, or you can get literally a crappy cable that's got the thinnest conductors known to man and be different, but both of them could still be $5 or $10. You can't assume these three categories are like this, but he basically says the price is a determinant of these three rankings, which, as you guys know that watched my videos and understand this field, price means nothing. It's what somebody decided to charge for a cable. What matters is the specifications of these cables, which he doesn't give us. He doesn't tell us the cable brands, because I was more than happy to go ahead and replicate all of his tests. Then I realized he hasn't identified anything. I can't go, what $50 cable, what $500 cable. So it shows you this absurd bias he has. And by the way, he's a high-end audiophile, and he keeps dragging this thing into his day job. His day job, he's a physics and astrophysics professor. It's nothing to do with audio. And he keeps wanting to use his everyday job to try to justify and do research on audio, high-end audio, prove that high-end audio has value. So, and he shows in here where he thinks more money means more quality. Anyway, he also picked a 2-meter interconnect cable, 6 feet. I use 2-meter cables too for ease of testing here, but a lot of you probably using 1-meter cable, and in the kind of testing he's going to do, this length matters. So why not test a 1-meter cable? Interconnects usually you're not going 6 feet apart. You have your amplifier or preamp or DAC pretty close together. Most people are not dangling a 6-foot cable, a 2-meter cable between them. So this is another bias where it's trying to do this. And And that's sort of implied later that these cables actually weren't even the same length, because he says it's compensated some of the parameters. They normalize them to length, which to me would be even more absurd if he hasn't matched the cable lengths. Excuse me. So then he starts this whole section and saying, oh, you don't want to use Roomy Q Wizard and audio interface to do this kind of testing. It's like, whoa, where did that come from? Once you get an audio analyzer like I have, that's how you do testing or proper equipment. Who's using, Ruby Key Wizard and a sound card? But even if you did, that's perfectly fine. 190 kilohertz sampling rate gives you 96 kilohertz bandwidth for audio. Is 4.5 times more than your hearing range. So it's perfectly fine. But he goes out and he says, hey, look, what you really want to use is a digital storage scope that goes up to 10 gigahertz single shot capture. Like, really? 10 gigahertz oscilloscope we need to measure 20 kilohertz? So we have 20 kilohertz, 1,000 times more than that is 20 megahertz, 1,000 times more than that is 2 gigahertz, or 20 gigahertz. So he's going a million times higher bandwidth he thinks we need to measure the an audio cable. It's like, where does that come from? By the way, my measurements are done, as most of you know, with Audio Precision Analyzer. It can go up to a megahertz bandwidth, which is plenty for audio, 25 times more than the bandwidth. And importantly, it outperforms all these fancy sounding equipment he's throwing at you, because it has 24-bit analog to digital converters. And whereas these digital scopes have 8 or 10-bit ADC, they also digitize the signal before analyzing it. But because they have to run at such high speed, you can't keep accuracy and a bit depth high. So the dynamic range of these scopes is quite poor. So whenever you give it a chance, you want to measure something with the least amount of bandwidth and appropriate tool. So I'm able to dig way deeper in noise floor and distortion with my analyzer than you ever can do with this. Now, if you're measuring cellular, transmit inside a cell phone and runs at 2.5 gigahertz, whatever, then you have to use this kind of scope, and that's and you give up dynamic range. But fortunately for RF work, you don't need that kind of dynamic range. He brags about this thing and hoping to confuse people, like, typical YouTuber who just sees it. So, whoa, wow, that's really fancy. Therefore, this is a big deal. It's like, no, he's gone to the university lab and grabbed a 10 gigahertz scope and said, let's use that to analyze things. It's like, no. You're using the wrong tool for the job. And I'll show later on how he's arrived at the wrong data, because that's what he's done. So he just quickly says, look, we've taken the cables and hooked them up between a signal generator and the scope. Wait a second, these are RCA cables he's testing. Look on this is the exact picture of the scope that they're using. And here's a 204 LXI from the Koroi. And look, they have BNC connectors. Every scope out there has a BNC connector. None have an RCA connector. RCA connector is the wrong kind of connector for RF work and radio frequency or high frequency work, and it's not a proper interface to use. So how did you hook up an RCA cable to this? You say, whoa, you can go buy little adapters. Well, you can, but that adapter at high frequencies can actually have impedance mismatch and cause reflections of its own. So while at audio rates it would not matter, and I use the same thing on my audio analyzer that has BNC instead of RCA, but if you're going to go test things at RF, then you better damn make sure that you use a proper RCA to BNC adapter and that you include that effect and subtract it from what you're measuring, because you could very well just be measuring the interface problem and the adapter versus the cable. The cable could be quite innocent. And so these are the sort of red marks, the red flags that I see as I read this paper and say, whoa, here's somebody who actually doesn't know anything about what he's doing in here, because no engineer doing RF work will try to take an RCA cable and hook up it to a BNC and then hook it up again on the other end, same way, and claim to be making very high frequency measurements and on this thing. So be very, very careful on this thing, that this kind of testing is just not valid, and it's a lot of hand waving going on. So he goes in here, and this one's done with a simple LCR meter, which is measures resistance, inductance, and capacitance of a cable. And he dumps these numbers. And first thing he does, which is a good thing, he says, by the way, if you just look at the resistance of the cable and then he computes it as a power rating with the units I've never seen of he creates this micro B scale of 0.00001 dB. When he uses that, he can then claim these are single-digit numbers in decimals. But in reality, if this 4.11 is actually 0.00004.1 in here. So this is an exceptionally small number, the power losses over this 2-meter cable, which is of course true because the resistance of it is only 47 million thousandths of an ohm. There's just the resistance is not a problem in an interconnect cable. Thankfully, he comes to his own senses and says, oh yeah, for this thing to matter, get a 3 dB loss, it has to be 11 kilometers long. Of course, it has to be that long to matter. So he dismisses that the resistance is an issue. But then he jumps on this whole transmission line effect and he says, hey, looky over here. And he creates this delta Z percentage, which I haven't seen. And he claims that, look, as I go from expensive cable to a cheap cable, things progressively get worse in this delta Z percentage, which I think is based on his propagation speed or some other silly thing like this. And therefore, this is a better cable. It's like, no, that's just a simple formula that he applies, and it's only true when you're entering in transmission line effects. And again, I could go pick another free cable and have it blow away his fancy cable. And I'm also putting aside that these measurements are correct. Measuring these small values correctly and everything requires real skill. Even things like how you terminate the ends. How do you connect an LCR meter to an RCA cable? The connections don't fit each other. So how you attach one, just the ending of it, how you attach that, how much torque you even put on it, how tight you make those connections, wildly changes this thing. It's certainly not work for a beginner to just jump in there and say, oh, we go to the engineering lab, get an LCR meter and hook up a 6-foot cable. How you even lay that cable, if you don't have it completely flat and identical. When I did a cable test with a speaker cable, I laid them perfectly in the exact same position on the table, so they're all measured exactly the same. You coil the cable or throw it around, they can pick up interference from the air, AM stations and others, and they can change the induction and capacitance just because the way you've laid them. So I don't take any of this to be correct anyway, but even if we did, it's like whoop-de-doo. There is no such delta Z percentage of these numbers in here to matter whatsoever. Okay? Excuse me. So then he does another test in here with 600 megahertz bandwidth testing. 500 megahertz bandwidth? We're not even at 500 kilohertz for audio, and you're jumping to 500 megahertz measurement of this thing? But then luckily he says, yeah, the amplitude in frequency response variation that they measured was only 0.03 dB. And therefore, the tonality cannot change. So he says, when people on audio forum says the cables can be frequency responsive, that's wrong. But then he goes and invents this thing called the subjective frequency response. That is the timbre or tonal quality of the sound through other factors investigated here. Like, really? There's a subjective frequency response? Who the heck invented this? I mean, it makes no sense to me. You don't get to invent that there's a frequency response that's imagined and it's called subjective. Just throw it out there and say, let's assume this is a fact, and let me now prove it to you through the following test. So let's say his following test. What is his following test? He says, all right, let's get a signal generator that's a pulse generator. What's a pulse generator? It means it generates these very precise square waves where you go and it comes back down. And he says, let's have it generate 5-volt pulses. And that, let's see, I'll get into the frequency of it in a second, but it's like analog audio, it's changing gradually. It's not a pulse, and it certainly doesn't jump from 0 to 5 volts and back to 0. That becomes a very high frequency signal, and yes, you better have proper cables, and the proper cable is not an RCA cable or ion audio cable. It's a BNC RF cable that you get, that you connect. You don't use RCA cables and rig the stuff to do this, okay? So what pulses is he generating? He sets the pulses to be 4 nanoseconds, narrowest possible pulse. 4 nanoseconds is 250 megahertz. You just invert that 1/4 nanoseconds and you get the frequency. He's measuring 250 megahertz pulses. That kind of bandwidth, they're going through this audio cable. And then he says, if we measure that, we see that, oh yeah, the 3 cables are ranked order again. The cheapest one is got this kind of rise time or latency, or whatever the heck he's calling it here. I think he thinks it's a velocity through the cable propagation. And one is here, the other one's here, and the other one's here. Therefore, it proves that this one's a better cable than this one. It's like, again, I can pick any, much different budget cables and have it produce something else. But why would I care about a 4 nanosecond pulse to go do anything? This cable will never, ever, in audio applications, be subjected to a 4 nanosecond pulse. Okay? So, yes, everything matters if you do have a 4 nanosecond pulse. A lot of things matter, and all 3 of these cables would be trash for doing something like that. But for audio, we don't do that. And by the way, proof point is try to push that 4 nanosecond pulse through your audio equipment or your speakers. You think what comes out is a 4 nanosecond pulse? No, it will be obliterated. There will be nothing coming out of the system. And if the rest of the equipment doesn't care and will do all these crazy things to the velocity speed, then what difference does it make what the interconnect cable is doing? The interconnect cable actually has got the widest bandwidth of anything between your audio cable. Interconnect cable can go to many megahertz easily, but your amplifier can't go to many megahertz easily. So why would it matter what this cable is doing between 2 pieces of audio equipment? But what's inside your speakers and those crossovers and those wires and all that stuff, none of that matters. The circuit put traces, and, the velocity, propagation, speed through those things don't matter, but it matters in the cable itself. It's just quite absurd. Okay? Then he gets into this noise thing that just boggles the mind. But so he goes back to 1 megahertz bandwidth, and without specifying whatsoever how these cables are laid, what the environment is, how noise sources are controlled or anything, he says, let's measure the noise, not just in absolute level, but measure the noise in the left and the right and see how they're correlated together, because depending on how they're correlated, they sound different. It's like, no, if the noise is exceptionally low, you can't even hear it. And if the noise is above audible band, you also can't hear it. I don't care if there's interference going into the cable at 200 kilohertz that goes into left and right the same way. That has nothing to do with audibility of correlated signals versus, in, let's say, in music, which tells us channel separation and sound staging, when it's real audio frequencies, not way the heck out of band. So let's see the measurements he does. He does this, shows this FFT. Again, these are the 3 cable, the S and M and G, and at least here nicely he says this is the 20 kilohertz limit. Then he shows the spectrum of junk, really. He's saying these things are the noises these things picked up. In here it says this is microvolts. 10 microvolts, that's huge amount of noise pickup. This is all garbage interference and noises in the source or the analyzer, because he's not using proper audio equipment. I've tested one of these free cables, throwaway cables, and I did a video on it. And this is my measurement of that, where that cable is transmitted in 1 kilohertz tone, which is this. And look at the only thing that's visible in here is actually the distortion from the audio analyzer itself at minus 150 decibels. This is down to nanovolts over here. Look at how clean this is. There's not a single all these spikes is showing in here up to 20 kilohertz, they would be up this high over here, and you don't see a single thing in here whatsoever. My largest spike in here is a mains noise at 60 hertz, which is minus 150 dB. So clean up your measurements. You don't go measure noise like this, and this stuff is just garbage. I mean, who knows? Maybe it's got fluorescent or LED lights that are just interfering with these cables. Again, you have to, have all the cables be parallel and properly set up, and how you couple the ends matters. Again, you go from RCA to BNC, you screw things up. So total junk science in here, junk everything. I mean, just mind-boggling that nobody properly even understands the basics of this thing. Look, he says, what the hell is this garbage you're showing? And by the way, he says this is the best, and this is the next best, and this is the worst. Well, that's not how it looks to me. Look at this medium cable. It's really far worse than this cheaper cable. So that screws up his thing. And by the way, AMC, which one of them looks better? I don't know. Both of them look bad, and there's nothing distinguishing this $500 cable from this, free $5 one. So based on his own things, this is wrong too. So this is his summary, not my summary. My summary will go out next. So it says the noise is available at audible levels. Yeah, if the noise is, 1 microvolt, depending on how much you amplify, it would be audible level. But you measured it wrong. This is the actual noise. There's nothing there. And, go ahead and hook up a normal interconnect to your system. Are you hearing hiss and noise because of the cable? No. You're hearing hiss and noise because your amplifier is making noise. If your speakers are very sensitive, your headphones are very sensitive. So this is just absurd. There's nothing even supported in a paper there's anything audible in here. You can't just wave your hand and say this on this thing. And again, I've measured tons and tons of equipment, and every DAC and preamp, everything else I measure is using an Amazon Basics cable, which I think is a $10 cable, goes through my analyzer, and I show that the instrument, whatever I'm measuring, plus the instrument's noise, plus the interconnect noise, is 1,000 times lower than what he's measuring. So clearly is measurement errors in there. But let's say we take what he's saying. He's saying, look, because there's an order in here that the cheap and the better and most expensive, when I measured certain things certain way, these parameters were in sync with that price difference. It's like, whoop-de-doo. What does that mean? It's not like you went and tested 10 cheap cables and found them all to be performing the same. Cables are different. It's all depends on what choices you made. Who knows if you picked different cables and got different results and you played with them enough to get what you want. Okay? So, and a lot of these things, by the way, even though it's put in the summary, it says, signal there's a triboelectric noise effect. All these things are in the summary. There's nothing in the paper about any of this stuff. Microphonic aspects of the cable, that's not in the paper. It's not measured whatsoever. What the heck are these things doing in the summary? If you don't summarize something, you don't introduce new topics at the end. So he continues and he says, prior work demonstrated audibility of these things, and that was because RF noise was the likely cause of the difference people perceived. RF noise? And again, no, there was no cause and effect in his previous study, and no way was RF noise proven to be the cause of anything in there. It was just something he measured some RF noise and claimed is lower in one versus the other. Whoop-de-doo. That's not the reason for any audibility difference in A/B testing. But, and yes, at high frequencies, cables become extremely important. The interconnects, terminations, everything becomes important. But audio is not high frequency. Audio is just, very close to DC. So what is my summary? If you didn't understand any of that, that's okay. Just when somebody says, check out this scientific proof, the answer should be, there's nothing there. As the saying goes, it's a nothing burger. The handful of measurements are performed that they sound fancy because I use this scope and that thing, and here's a bunch of formulas and everything. The measurements are trivial. They show that the author doesn't understand the tools he's using, doesn't understand the topic. Yes, he has a PhD in physics and astrophysics. I'm sure he could write papers in that domain that I wouldn't be able to even understand what he's talking about. But this is my domain, that of engineering. This is what I understand. This is what many engineers understand. And they would just laugh at what he's trying to do. He just talks about and writes things in a way that clearly indicates he went and borrowed a bunch of electronic things from the engineering lab and made some measurements. But he should have talked to the engineers in that department and the professors there and say, hey, what do you think of what I'm doing in here? And they would have schooled them well. So lots of warning flags that what he's doing is that he's going outside of his field of expertise, and he's no different than a hobbyist with access to some gear in a university lab. And he claims there's some timing effects with 3 random cables. Again, you want to prove that? Great. Give me the brands and models. I'll go ahead and retest them properly. Let's see even if your measurements are correct, let alone the conclusions you draw on them. And what effect he does show on these 3 random cables is at megahertz and gigahertz, which we absolutely do not care about. He then makes random connections to audible effect. None of that is in the paper. The paper is just about measurements. There's a bunch of references. Oh, here's reference number 35, says what I'm saying is here is true. It's like, no, absurd nonsense. You want to say there's some audible? Go ahead and show me the psychoacoustic analysis of 4 nanosecond pulse. How is that, what aspects of that is audible and what? And please don't think there's science here, there's research here. There's nothing in there. There's no science in here. There's no research in here. This is just a bunch of hobbyist level measurements, as I mentioned, of a few parameters of a cable to say, hey, can we find a difference? Yeah, you don't even need to do any of this stuff. I show measurement differences even in, well below megahertz. We can show differences in the cables. The question is, where do they land? Are they audible? And by the way, is it in favor of the expensive cables? No. Many times I measure these cables, find that it's the expensive cable that picks up more noise, picks up more interference, not the cheap one. So bottom line, it just, there's nothing there. Anybody who throws that YouTube at you or that paper, just point them at this thing and say, if you don't understand it, the video I just did, then stop. Don't believe stuff just because you like the, punchline that's thrown at you. Okay, hopefully you handled this 41-minute video. It's a lot of work putting this analysis together, but I thought I'd do it once and shoot a video. Okay, see you in a future one. Bye-bye.